Yo, what's up guys? I have a super exciting video for you today. I'm up in Joburg at the InDor LED manufacturing facility. We're going to get a tour, we're going to find out what their lights are all about, we're going to look at all the things they're doing to make sure that these lights are quality, that they're spec towards the South African market specifically, and just get as much knowledge as what we can. I'm going to meet up with the InDor guys now. Let's go!
This is where we actually put LEDs onto printed circuit boards for various applications. The process starts with a screening process. So for example, we start off with a blank LED board like this. It's got nothing on it other than its silk screening and its solder points. What we now need to do, the first step is to actually apply solder to the solder points of the board. Mike, you can just take them through it.
But here what's called a stencil printer, a manual stencil printer. Okay, it's called a manual stencil printer. Okay, we've got a stencil that is cut, laser cut out of stainless steel. And these points correspond exactly to the points on the board where we need solder. Okay, so how the process works, I'm going to take the solder paste, which is in a liquid form, and I am going to squeegee it on. Okay, so that takes exactly the right amount of solder paste, exactly through the apertures where it needs to be. Okay. So now you'll see the solder paste, exactly the right amount in exactly the right places. I can now inspect it. If I'm not happy with it, I can stencil it again, but this looks pretty good. From here it will go into the machine. So this is a pick and place machine. It's got 3 heads that it will pick up with. So each of these heads will pick up either an LED from this feeder or a resistor from that feeder. So we close the door for safety. Now we go to the software. When I click on start, the machine will now look for alignment points on the board. Found one, found the other alignment point. Now it will pick up nozzles, okay, and then pick up LEDs and place them.
As it places, you can see on the screen the black dots start to get filled up. That's the bottom at the moment. This machine can place up to 12,000 components an hour, depending on the complexity of the board, the number of LEDs, the amount of feeders we line up. 12,000 parts per hour, and it does it with great accuracy. Mike will visually inspect the board to see that everything looks okay by eye. If it does, it goes into the oven. Because we used a wet solder, we now need to evaporate the solvent, and we need to do it in such a way that it doesn't create bubbles and lift the LED off the heat pad. So the machine itself, the oven itself, has got 4 chambers. So zone 1, we're going to heat up the board gently. Zone 2, we're going to evaporate the solvent out of the solder. Zone 3, it's going to cure. Zone 4, it starts to cool down and it comes out here and drops off. So that board that you saw being made, that's what a finished one now looks like. The primary LEDs that we use in horticulture are the Samsung 301B. Since they launched that little LED, Osram has caught up, Salt Semiconductor has caught up, and we use some of their LEDs as well. But the base model still remains the Samsung 301B. It's still the class leader in producing a sunlight spectrum, what plants need. We then augment by adding far red for flowering. We use true far red. We measured with a spectrometer at 730 nanometers. That means they take temporary power, they switch them on, they check that everything's working. It then goes to the various shelves. The function of this device is to measure the total amount of light emitted from a product in all directions. So if you want to go around to that side, what we're busy testing at the moment is we're testing one single UVC lamp that's being used to combat COVID. We're measuring this lamp over a 9,000 hour cycle. At the moment we're at 4,000 hours, and what we're measuring is the depreciation of the light over time. Because we're making a medical product here, we have to be able to produce the right amount of UVC for the product to do its job. We need to know that the manufacturer's claim of 8,000 effective hours is real. So we're double checking them. So if you go to that side, so inside here is a 55 watt UVC lamp that we're busy testing. We're at the 4,000 hour mark. Over there is the aperture where we put the light meter. We shield the direct light because all we want is the reflected light. This is not normal paint. This is a special kind of paint. What we've established with this particular lamp over a 4,000 hour period is that we've had a 6% loss in light over the 4,000 hour time. That's well acceptable. At the end of 8,000 hours, we're expecting about a 15% depreciation of light. It's acceptable, it's within specification. Every single product that we make has a surge arrestor built in for South African conditions. That little device is designed to capture any excess voltage, any transient spikes caused by load shedding. An electrician drops a neutral by accident, puts 380 volts through the light fitting. That little product there is designed to capture it and save everything downstream of it. So it'll save the power supplies, it'll save the LEDs.
Wow, that's very unique.
And this is in every single product. It's a German product manufactured in Serbia. It's got surge protection, but it's only got 1 kilovolt. That's 1,000 volts. This particular device has got 20,000 volts of surge protection. So it's much more robust. It also gives us a smoking gun should something go wrong. So when the product comes back and that product has failed, we know what happened. We don't need to look further down the line. We can tell the client, sorry my friend, you dropped a neutral or you had a surge. So this product will capture roughly 9 to 15 events before it fails. So you can make a mistake, you can have a surge 15 times, you won't know it's happened because the light fitting will just keep working. But at a point, it will also fail. And then you have to replace the surge protector. This is it's most developing countries have a similar problem. So it's being assembled at the moment, so that's why the wires and that are still loose. But what we're going to show you now is the process known as metal spinning. Take that piece of aluminium and turn it into that. Obviously not powder coated yet. Come to this side. Don't even smile, you're on camera now. That's now the finished product, which will now go for powder coating. If you don't know what you're doing, you'll tear through the metal. If you push too hard, you'll rip it apart. If you push too softly, it'll have bubbles and ripples in it. So a guy like Joan has been doing this for a long time and he's highly skilled. I can't do it. And we'll run them for a prescribed period of time. So those are being burned in at the moment. Those are the same fittings you saw downstairs. There was a power supply here, and the one that you filmed actually had an emergency battery pack over there.
Yes.
That's the product before it gets labeled and packaged. This is a photogoniometer. The purpose of this device is to measure the performance of a light fixture in given angles on an X, a Y and a Z axis. 7.4 meters away is a calibrated light meter. That's a locally manufactured light meter made by Goldilocks, by the CSI, named Goldilocks, manufactured by the CSIR. Let the light fitting warm up for half an hour, so it gets to full temperature. Because LEDs decrease as they get warm, it doesn't help we measure this thing when it's ice cold. We keep the room at 24 degrees when we are doing tests. That's the industry standard for light fitting tests. It's 24 degrees. That's known as the average ambient light level. So what Wolf will do is after half an hour, he will set it at 0 and he'll take a reading from the light meter which is positioned over here. Wolf, you're going to have to get a torch. There's the light meter over here. He'll write down the reading at the 0 degree mark. He will then move this contraption 5 degrees and he'll take another reading. He'll move it 5 degrees and he'll take another reading. And you keep doing that till you're through to 90 degrees. And that gives you one axis of your polar curve. To get your next axis, he repeats the procedure in this axis. So it's a long, onerous procedure. If the light fitting emits light backwards, we can actually do a Z-axis as well. That's why this gimbal over here is also rotatable through 360 degrees. That information is then captured in a computer program known as Toolbox, which then allows us to generate what's known as an IES or an LDT file. These are simulation software packages that enable somebody with lighting software to use our product and design a lighting installation. It could be an airport, it could be a grow room, it could be a shopping center, it could be a car showroom, it could be a hospital operating theater. And we guarantee to be accurate within 8%. What we have no control of is colors of walls, colors of floors, colors of ceiling, reflection, and so forth and so forth. That's up to the user of the software to input into his information when he's doing a simulation. So, this is something that very few lighting companies actually have. In South Africa, probably 5 or 6. That's it. And we do our own measurements of everything. Nothing is taken for granted. If I tell you the light fitting produces this, it produces that. Interestingly, we can self-calibrate as well. And to do that, we use what's known as a reference lamp. So for example, this is a reference lamp. This old archaic Siemens lamp is worth about 17,000 Rand. The reason is because they only made 900 in the world, and the product produces a given amount of light at a given voltage, and that's guaranteed. So if we in any doubt as to whether our equipment is still accurate, short of picking it up and sending it off to the CSIR for recalibration, which we do every year, Wolf, he can take this, he can put this in the sweet spot, he can switch it on at the correct voltage, and he can double check what the results are. And the calibration certificate for a product like that looks like this. Luminous intensity lamp manufactured by Siemens, and it's the National Metrology Institute of South Africa, which is a division of the Council for Scientific Industrial Research. So everything's traceable backward and forward. X-axis would be this axis here. We would move along this gimbal in 5-degree increments. And every time we move it, we stop and take a measurement. So we move it 5 degrees, 15 degrees, 20 degrees, oh that's 10 degree increments, 5, 10, 15, 20, 25, all the way through to 90 degrees. When we design an LED board, and I'm actually going to take, this is a horticultural board. There's the far red, and there's the sunlight white, the Samsung 301B. When we design a board of this nature, we have the luxury to be able to choose the amount of, first we have the luxury to be able to choose the base material, which can be FR4, which is a type of fiberglass, or it can be aluminium. Just find one like that. And the decision whether to use aluminium or FR4 depends on the power density of the individual LED. In this case, these big LEDs over here produce up to 8 watts each. And so the power density around that little area is extremely high. And I'm not sure if you can see, but I'm going to tilt it at an angle in an attempt to get you to see the amount of copper pore we leave behind. The reason we leave the copper pore behind on the printed circuit board is because it takes the heat out of the LED very, very quickly. And when you are designing a printed circuit board, the entire printed circuit board is covered in a layer of copper. The printed circuit board manufacturer strips the copper away with chemicals to give you your tracks. You're paying for the copper. Leave it there. Leave as much of it there as possible because it acts as a heat sink. So we leave as much copper as we can and we only strip out what we need to. That's the first step. The second step is when we then decide, okay, we've got a new board, we're going to take it to market, but we first need to finish the testing. We need to test the operating temperature. So we'll go to an area, set it at 24 degrees, we'll put the board in its housing, we'll solder a thermocouple somewhere in the center of the board where we believe it'll be the hottest. We'll solder it very close to a central LED, very close to the heat pad. We then measure the actual temperature of the LED, the real temperature, what's known as the junction temperature. And we try to keep that junction temperature under 70 degrees. Typically the LED is designed to operate up to 120 degrees junction temperature, a Samsung 301B. So by keeping it under 70 degrees, we're running it at 50% of its red line. Coupled with that, the LED is designed to be able to handle up to 230 or 250 milliamps. We don't run higher than 170 milliamps. Our idea to get the light volume is to put enough LEDs to give you the volume rather than over rev the fewer LEDs in a cost-saving exercise. So does that make sense?
They'll last, let's get in here, they'll last then longer because they're not running at 100%, or you're not putting as much strain onto each individual LED to get power.
And you're keeping it cool.
Yes.
Those are the two things that will kill an LED, heat and overcurrent. And we try and keep those under control. Over and above that, I won't use an LED unless the manufacturer can give me an LM80 test report. Now, an LM80 test report means lumen maintenance 80% at the end of a given period. So if I say all our products are tested to LM80, that means at the end of 50,000 hours, you will still have 80% of the light that you started with guaranteed. We do a lot better than that. But that's an industry standard. Now 50,000 hours translates to 5 years at 24/7. So at the end of 5 years, you'll still have 80% of the light you started with. That's our manufacturing criteria. Most people have no idea what that even means. We have to be able to do that. If we do a farm, we can't have the product depreciating in 2 years and the crop starts to, you need to produce the amount of light you started with or as close as possible for as long as possible.
Super important to keep the environment the same, so you can't have fluctuating levels the whole time. Otherwise your product's not going to adhere to the standards, you know what I mean?
And that's the biggest issue with HID. HID falls off a cliff after a period of time, which LEDs don't. Having said all of that, HID is an old, tried technology, and I don't dislike HID. It was my bread and butter for many, many years, and they're good products but LEDs are way more efficient. They're just a bit more sensitive. That's why we have to put the surge protection and so forth in.
Thanks for checking out my tour of the InDor Sun facility, guys. I was really impressed with how much testing was being done and how much attention to detail they are doing. We're also going to be supporting them as our Marijuana SA brand, so you guys can check that out soon. But for everyone watching, please remember to subscribe, please remember to like, and as always, check out the Patreon if you're interested in supporting our journey a little bit further. But till next time, guys, peace out.